I want to just start off today by finishing our discussion of differential equations. So this is a topic that we'll come back to lots more times. As we're doing applications, we'll often need to know a little bit more about differential equations, but we've talked about some of the most basic types so far. Actually, often when we're doing applications, the variable y will actually not be a function of x, but you should think about it as a function of time. So t is always the variable time. And then the derivative dy by dt would often be denoted just by y dot of t, or even just y dot for short. So dot is time derivative. That's kind of a tradition rather than anything else. So it's just the same as the prime we were using for derivative before, but the tradition is to use a dot for time derivative. And then d2y by dt squared, the second time derivative, that'll be y double dot of t, or simply y double dot. That's the second derivative. And let me see. So I guess one of the first things that you learnt when you were probably in maybe middle school or high school, but long ago, you would have learnt that time is distance over speed. So when I learnt this when I was young, I used to draw a little triangle for these kind of trivial physical relationships. That there's lots of them. Time equals distance over speed is one of them, and so I would always draw this as a little triangle. It always helped me just remember what was going on. It's just a little shorthand. Time is distance over speed, and then you can read this in different ways, right? Time is distance over speed. Speed is distance over time. Or distance is time times speed. So that's that. Just rearranging that formula. So I know that's a very silly, trivial thing, but speed is like miles per hour. Speed is distance miles over time per hour, or meters per second would be a better choice of unit, really. And when you were learning that sort of thing, maybe this was in some very beginning physics class or something like that, you would have probably drawn a time against distance graph. So you have maybe there's the origin at time 0, you're at the origin, and y is how far away you are from, maybe the origin is your home, so how far you've traveled from home, and you might leave home and you might start walking at some constant speed, and then you might start running and then stop, and then you might kind of slowly walk home again or something like that. So the slope of that, well, right there, right, that's when you're walking at a constant speed. Slope of that line, that's slope, so that's rise over run. So the rise is the distance you've traveled and the run is the time. So the slope is the speed, distance over time. So slope in a distance time graph is the speed. Actually, we should say velocity, because it could be positive or negative. So you use the word velocity for speed together with a sign that remembers whether it's forwards or backwards. Okay, so the slope in a distance time graph is velocity, and that makes sense even when you're not going at a constant speed. When you take slope, you would take the tangent slope, because that would be the instantaneous velocity at some point along the curve there. Okay. So this is meant to convince you that if y is displacement of some moving particle, so y of t is how far it is away from the origin at time t, then y dot, the time derivative, is velocity. And often you just use that, you call that rate of change. When it's time derivative, rate of change is a synonym for time derivative. So velocity is rate of change of displacement. y double dot is acceleration. Acceleration, its rate of change of velocity. Okay, so derivative, when it's time derivative, is very useful for talking about motion and velocity and acceleration. This is very natural. So I just was going to do one kind of slightly silly example, but I think it's fitting at this point in our study. So let me try and draw a tree. There's some tree. And up in the tree there is an apple. And standing underneath the tree down here, this would always be Sir Isaac Newton. And I want you to imagine that that apple is 3 meters above Sir Isaac's head. So let me see, at time t equals 0, the apple falls from the tree. And the question I want to address is how long, how many seconds before the apple hits Sir Isaac's head. Okay, so this is a very simple situation where we can use some differential equations. The thing is that gravity of the Earth, exerts a force on the apple which accelerates it downwards. So I guess the basic law, one of Newton's laws which we're using, is the law F equals ma, force equals mass times acceleration. So the mass here would be the mass of the apple. Actually, the mass is kind of irrelevant here because the force that the Earth exerts on the apple is mass times the acceleration, which is constant near the Earth's surface. So let's write that. Near the Earth's surface, the acceleration due to gravity is roughly a constant. You should always treat it as being a constant. And that constant is little g, which is roughly 9.8 meters per second squared. So that means that the force on the apple is mg, where m is the mass of the apple. So let's make this a little bit more readable. So that's our basic Newton's law that this is all about, this example. F equals ma. So near the Earth's surface, the gravity makes things accelerate at this constant acceleration, 9.8 meters per second squared. So the actual force on the apple would be mg, where m is the mass of the apple. So now what we're going to do is we're going to let y of t be the height of the apple above Sir Isaac's head at time t equals 0. So I'm just doing a very basic, simple thing. So what we know is that at time 0, the apple is exactly 3 meters above. So y of 0 is 3. That's our initial condition. And then the laws of physics tells us that the acceleration, which is y double dot, the second time derivative of this height, is constant. It's this number g. Actually, we should write minus g, because we're measuring height upwards, but it's accelerating downwards. The height is getting smaller over time. Okay, so that's the basic physical law that we're using the acceleration of the apple, y double dot, is minus g, this physical constant acceleration due to gravity near the Earth's surface. So all I'm really trying to do with this example is just start getting used to thinking in the most simple way about laws of motion and some basic physics, because that's where all our applications are going to be in the first half of the course for sure. So y double dot is minus g. So what can we say? So this is a second order differential equation. We saw such a thing in the last lecture. So what do we know? Well, we know y dot has got to be an antiderivative of minus g, but now with respect to time, right? So that would be minus gt plus a constant. But let me see. We can work out that constant because we know that when t is 0, the velocity y dot of 0 is 0. That's the instant the apple breaks loose from the tree, so it's not actually moving at that instant. The velocity is 0. So that tells us what 0 is minus gt. I'm plugging in t equals 0, so minus gt is just 0. 0 equals c. Okay, so actually y dot is minus gt. Hence, so now we've got to integrate one more time. We've got to take antiderivatives. Y, which is what we're after, it's an antiderivative of minus gt, so that's add 1 to the power, divide by the new power. T is the variable here, minus a half gt squared, plus some new constant d. But when t equals 0, we know that y of 0 equals 3. So when I plug in t equals 0 in that equation, 3 equals d. So actually, y is 3 minus a half gt squared. So let's put a little box around that so that you see that. So that's our particular solution of that second order differential equation. Okay, great. So now the question we're asked to solve is how long does it take before it hits Sir Isaac on the head? We want t, so y of t is 3, right? We want to know at what time t is the height of the apple. Sorry, not t. Y of t is how far it is from Sir Isaac's head, so we want to know when y of t is 0. That was the way I set it up. We want the time for which t is y of t equal to 0. So we want 0 to equal 3 minus a half gt squared, so that time when it hits Sir Isaac on the head. So let me see, I just bring the half gt squared over to the left. I need to times by 2 and divide by g. I get 6 over g, that's t squared. I need to square root it. So g is what, about 10, 6, so 6 over g, it's a little bit more than 0.6. That's pretty close to 0.64, I would guess, and 8 eighths is 64, so that's roughly equal to about 0.8 seconds. That would be my final answer, roughly. I think that's to about 1 decimal place. This is not a bad estimate I just made. Okay, so that's how long he's got to get out of the way to avoid the apple hitting him on the head. All right, so that was a very simple differential equation. That was the basic differential equation that we're looking at there. That's the differential equation for motion under constant acceleration. So this is kind of one of the first things that you do in beginning physics. And we worked out the velocity and the displacement in terms of time in that way, and we used the initial conditions to resolve we needed 2 initial conditions, y dot of 0 and y of 0, to get the particular solution, telling us how high the apple was over all time. Okay, enough differential equations. That's just a silly example, but hopefully gives you just enough little bit of physics that I'll be able to get more sophisticated with our physical applications soon. So where are we? Let's just have a brief recap. So at this point I've talked about derivatives in Leibniz notation dy by dx, and I've talked about antiderivatives, also called these indefinite integrals. Remember, this was just my notation for some function of x whose derivative with respect to x is the function y. So that was a bit of a weird notation using this integral sign. I haven't really explained where that comes from, that notation, why it's done like that. That's what I'm going to do today. It's worth pointing out just before we go anywhere, just given the function y, the derivative may not exist. For the derivative to exist, the graph of y has to be a nice curve so the tangent line to it makes sense everywhere. So the right word that you use for the derivative to exist, you need y to be what's called differentiable. I don't think I used that word yet, so there it is. Differentiable is if that limit that defines the derivative exists. And similarly, y may not have an antiderivative. You need y to be what's called integrable. So if you have some really crazy function, there won't be an antiderivative. But actually, there's plenty of functions that you meet all the time that are not differentiable, but most reasonable functions are continuous. And we'll see that today. We'll see in particular that any continuous function is integrable. In fact, any piecewise continuous function is integrable. There are many more functions that are integrable than that. So being integrable is rather a weak condition. Being differentiable is fairly strong. It's stronger, for example, than being continuous. Maybe it's worth just reminding you of this notation one more time. That notation, integral y dx, it means a function whose d by dx is equal to y. So it may not exist, but if it exists, if that function y is integrable, this antiderivative, it's actually not unique. It's unique only up to adding a scalar c. So we talked about that antiderivatives. You need an extra piece of information to uniquely work out what that function is given some initial condition. So that's roughly where we are. Now the main topic today I want to tell you about the definite integral. So here's how this goes. You see, when we started doing... Oh, I can't spell whereas. Let's see if I can spell whereas. There we go. Whereas derivatives started from the idea of slope, integrals start from the idea of area. And I mean, when you see these two notions, area and slope, they're seemingly unrelated. I mean, they just seem like different concepts. You wouldn't think the one had anything to do with the other. So let's talk a little bit about the idea of area, and then we'll get to the fundamental theorem of calculus, which actually shows you that this definite integral is related to antiderivatives, hence to derivatives. So in fact, there is some connection between the idea of slope and the idea of area. It's a little bit of a surprise. So we've got to think about area. So what do we know about area? Well, I guess the most basic thing we know about area is the area of a rectangle. There's a rectangle. Oh, let's not shade it in. I don't really want to be shaded in when I'm drawing a rectangle. So here's a rectangle. So if it's an A by B rectangle, the area is A times B, the product of the two sides. I guess you know the area of a triangle. That's another easy thing. Let me draw a triangle. So here's some triangle. That's not a very good triangle. I'll try again. Triangle. There we go. So if that's the perpendicular, then that would be the height h, and let's let that side there be B for base. And let me see. You know that area, because what you do is you can just sort of fill it up to being a rectangle. So you sort of doubled that triangle on the left. I've added an extra copy of it up above, and similarly I've doubled that triangle there. I've got an extra copy of it up above. So I've just doubled my area, but I've made it up to a rectangle, and that rectangle, its area is the length of the base times the height of that rectangle, so BH. So the actual triangle, well, it's half of that rectangle. Okay, so the area of a triangle is half base times height. Of course, you all knew that. But the question is, how do you make sense of area for more kind of curvy shapes? So you might have some sort of curvy shape. What do you mean by its area? And so this is something that you understood probably in elementary school. And in elementary school, I expect you spent some time drawing shapes on graph paper with little square grid. And you would have just counted those little squares, little baby squares, to estimate the area. Of course, the finer your graph paper, the better it gets. If you had really fine graph paper, counting the squares that were covered by your shape would give you an even better estimate of the area. So the finer the better. And remarkably, that very simple idea, that was probably how area was first explained to you when you were young. That very simple idea is exactly what one tries to do mathematically. So here's the definition of a definite integral. So let f of x be a function. Actually, it should be an integrable function. So I guess my definition is a little wanting because I'm not telling you exactly what I mean by integrable. I'm trying to be just that little bit intuitive about what we're doing. And let's assume this function is defined on domain AB, so some closed bounded interval of the real numbers. Maybe it's useful to give you a picture of a function to kind of think about what's going on. So here's x, here's y equals f of x as usual, and I've got some graph. I don't know, it doesn't even have to be continuous, this graph. It might have jumps in it. It might go kind of like that, and then it might maybe jump down here, something like that. So there's some function, and I've got some interval a, b. So we're kind of looking at this strip of that function. And I'm going to define the definite integral so this is the notation integral a, b. So it has these limits. The lower limit a is the left-hand edge of our domain. The upper limit b is the right-hand edge of our domain. Integral from a to b, f of x dx. It's defined to be the area under the curve that's above the x-axis and it's to the right, so maybe it's in between the lines x equals a and x equals b, which are those two blue lines I've drawn in my picture. So area below the x-axis counts as being negative. Okay, so this example that I've drawn here, so this definite integral for this function, for this a and b, it would be that area counted positively and that area there, because that's below the x-axis, counting negatively. So it would be that part minus that part. Okay, that's what that definite integral calculates. I'm sure you've seen that definition before in your first course in calculus. Remember, I'm still in my first week when I'm just reviewing stuff that you've already seen, just refreshing your memory. So how would you calculate this? This definite integral. You cut the interval AB into thin strips, each of width, well, delta x, so some positive but small width, and then you add up the areas of all the strips. Okay, so I'm just being informal. I'm not trying to make really precise definitions because this is just a review. But let me see. This might be the strip at x. So it might be that. So here's a little thin strip. The function might be just sort of some curve there, and there's the x-axis, so this would be x, and this would be a little bit further along the x-axis, x plus delta x, and there's our little thin strip. But approximately, it's approximately, if this, so this is 0, and this is the value f of x, right? So that strip, it's approximately a rectangle. Of area, well, the height is f of x and the width is delta x. That works if you're below the axis, that value f of x is negative, so that area of that rectangle is counted as a negative area. So that was what I was saying earlier. Area below the x-axis counts as negative. That works out right. And so then what you've got to do is you've got to kind of add up. So this is the this is the sigma, meaning sum. You've got to add up the areas of all those rectangles as x goes from the left-hand edge to the right-hand edge. And that will give you an estimate of the area under that curve that we're after, this definite integral that we're trying to compute. And the idea is that as that delta x, as that width of the strips gets thinner and thinner, that's like drawing your picture on finer and finer graph paper. The error, there's some error, right, in estimating the area of that under that curve on that strip as the area of that rectangle. There's a little bit of error, but as the delta x gets smaller and smaller, as that rectangle gets thinner and thinner, the error goes to 0. So actually what you have to do is you sort of have to take this, and then you have to sort of take the limit of these sums, these estimates, as the width of the strip goes to 0. And so you take those things, and then you take that limit as delta x goes to 0, and that limit is this thing, integral ab f of x dx, the exact area that we're calling the definite integral. So that limit may or may not exist. Roughly, this word integrable, which I'm not trying to carefully define, roughly means that this limit exists. So there are some pathological functions where that limit doesn't exist, and those functions are not integrable. You can't make sense of area. But we won't really see any of those functions in this course, so we're just kind of staying intuitive, and I don't need to give you the rigorous definition, I think, here. Okay, so that's the definite integral. It's sensible notation. The idea is it's this limit of this sum, and the idea of the integral sign, this is sort of this sigma, which is sum, kind of in the limit, the sum becomes, in the limit, the delta x becomes the dx, and the sum becomes the integral. Okay, so now this is something very concrete and precise, a very, very formal thing. It's just a number, depending on the function and what a and b are. It's the area under the graph of that function between x equals a and x equals b. And giving you a little bit of clue how you would make sense of that. It's just the elementary school idea of cutting it up into little thin strips and adding up the areas of the strips, but sort of doing it in the limit as the width of the strips gets smaller and smaller. So that's the definite integral. It looks nothing like derivative. It's an honest definition based on the idea of area. So now we can talk about the fundamental theorem of calculus. So this is the big moment of enlightenment, which I always view as the real birth of calculus. So this is usually attributed to Newton and Leibniz, kind of independently. So this was roughly the sort of 1670s. Actually, Newton, I think, was first. I'm British, so obviously I'm a little bit biased. I think it was 1665 and 1666 when Newton came up with these ideas. So these were two remarkable years in Newton's academic life, where he did a phenomenal amount of mathematics, including all of this stuff about calculus and laws of gravity and planetary motion and all these things that you're going to be seeing from Newton in the next couple of weeks. It's kind of worth noting that these 2 years Newton was confined to his village in quarantine because those were plague years in Britain. So in those 2 plague years he really did a vast body of truly revolutionary research. So here's the fundamental theorem of calculus. So I'll give you readings about Newton and Leibniz, and you'll find out a little bit more about the history of this. I'm just going to mutter about it in the lectures and leave it to the readings for you to learn about this, but that'll come in the next few weeks. So here's the fundamental theorem of calculus. It says let f of x be a continuous function on some closed bounded interval ab. And then I'm going to introduce a new function which I'm going to call capital F of x. So I'll often call this new function the area function. So this means the integral from a to x. So this is a definite integral, but so the kind of clever thing is that I'm not putting b at the top here. I'm putting x at the top. So I'm making that right-hand edge of the interval where we're calculating the area, I'm making that vary. So this is a function of x as that right-hand edge changes. Okay, so hang on. So back in the previous slide when I defined definite integral, I had from a to b, and then I used f of x dx. But I've just put an x in the upper bound of my integral. So I can't use the letter x again. X is already used up, so I better use some other letter. I think I'm just going to use t dt. So this t here is just kind of a dummy variable, as x is in use at this point in the proceedings. Okay, so that's not a big deal. I'm just switching to a different letter so that I don't have too many x's. I can't use x because it's already used up in the limits of our integral. Okay, so it's the area under the graph from a to x. This number is the area function big F at x. And then the fundamental theorem of calculus says that the derivative of this big F is the little f for all x in the interval ab, i.e. big F is an antiderivative of little f on this interval. So this shows in particular that all continuous functions I had this hypothesis at the beginning that it was a continuous function in my statement of the theorem. It shows that all continuous functions possess an antiderivative. All continuous functions are integrable. I said there were some pathological functions which aren't integrable. Continuous functions are not pathological. All continuous functions are integrable, even something like just piecewise continuous, like there's 5 or 6 different continuous functions with a few jumps. But many more functions than that are integrable. Being integrable is rather a weak condition. So there's the fundamental theorem of calculus. It's not too hard to state. And I want to just explain why it's true. So this is not really a complete proof. But I want to give you the idea of the proof, and it's not too hard to take this idea and actually make it into a completely rigorous and complete proof. So all you have to do is you have to take this area function, big F, and we've got to calculate its derivative, which you do using the definition of derivative. It's the limit as delta x approaches 0, big F of x plus delta x minus big F of x all over delta x. So that's what we've got to calculate. That's what derivative means. So let's plug in the definition of what big F is. It's the integral from a, so I've got to plug in x plus delta x, f of t dt, and then f of x, so that's going from a to x, f of t dt all over delta x, which is the limit as delta x goes to 0. So now this is the area under the graph between a and x plus delta x. This is the area between a and x. So that difference in those areas, that's just the area from x to x plus delta x. And then this, roughly speaking, if delta x is very small, roughly speaking, this area, this is just one of our little strips in our picture. The height of the strip is f of x. So I'm still calculating the limit, so I still need to write lim. The limit as delta x goes to 0. Inside that limit, roughly speaking, what the area is in this little thin strip, it's roughly the height of the strip times the width of the strip. So that's estimating this thing, and as delta x gets very small, that becomes very accurate. And then I've got to divide by delta x. But now those guys just cancel. And so there's no delta x's anymore. That limit as delta x goes to 0, well, I've just got f of x. So it's just f of x. There's the limit. I cancel the delta x's. Now the limit's just f of x, which is what I was trying to show. I showed that the derivative of big F is little f. And the only reason this is not quite rigorous is that to make this into an actual bona fide proof, you have to make this step precise. This approximately equals. The rigorous proof here needs to use the definition of continuous at this point. And we're not going too much into those formal mathematical definitions of these things, so I can't give you the rigorous proof. Actually, strictly speaking, you need to know that a continuous function on a closed bounded interval, or on the interval AB, is what's called uniformly continuous. So if you maybe you took a more proof-based class and you would have heard the phrase uniformly continuous, or if you go on and take a course in analysis where all these proofs are given, you'll come across the notion of uniform continuity. That's really what it's all about, this proof. So there we go. That's the idea of the proof. That's all that's going on. You just calculate the derivative of the area function, and you make this one estimate. You estimate the area of a thin strip as f of x delta x, and then you can calculate this limit, and you get your little f of x back again at the end. So that's the fundamental theorem of calculus. That's the idea of the proof. Let's write down a corollary of the theorem. So the corollary says that if f of x is continuous on AB, and you know some given antiderivative, well, that's just what that notation meant, right? When I wrote this indefinite integral, that meant an antiderivative of f of x. But I really want you to have that antiderivative in your hands, so you know explicitly what this function is. You've got some explicit function in your hands whose derivative is the little f of x you started with. And then the corollary says that the integral from a to b, f of x dx, so that's the area under the graph, the definite integral, is equal to that given antiderivative that you have in your hands evaluated between a and b. So that's a notation I haven't used before, so let's quickly say what that means. If you have some function g of x, when I put square brackets a, b around it, that just means you take the value of g at the top, subtract the value of g at the bottom. Okay, so what I mean here is you take your given antiderivative, you plug in x equals b, and then you subtract plugging in x equals a. Right? So you do the antiderivative at b minus the antiderivative at a. That calculation in that explicit function, that's your known antiderivative, that calculation gives you a number which is exactly the area under the graph. So this corollary really connects definite integral, that's the thing that by definition is the area, that's this left-hand side of this equality, to indefinite integral. That's that thing, that antiderivative. That's the right-hand side, that's that given indefinite integral. So it says if you know an antiderivative of f of x, you can calculate the area. Okay, so the corollary is very easy to prove. Let's quickly prove the corollary. So let me see, just so we don't get lost here, let's let g of x be short for the given antiderivative. Right, so that's the given antiderivative of f of x. And let's let big F of x be that area function as usual. So that was this integral from a to x f of t dt. So the fundamental theorem of calculus tells us, because our little f was a continuous function, it tells us that this big F, its derivative is little f. The derivative of the area function is the original function. But g of x is another given antiderivative of that function. So we know that the derivative of g of x is little f as well. So that tells us that big F of x and g of x, they're both antiderivatives of the same function, so they're both equal up to a constant. Okay. So now we have to find what c is. Well, to do that, I'm going to plug in x equals a. What's f of a? That's the area from, I'm plugging in x equals a. That's the area under the graph between a and a, which is, of course, 0. I'm looking at this equation, I'm plugging in x equals a. The left-hand side, f of a, is 0. The right-hand side is g of a plus c. Therefore, actually, c must be negative g of a. So now we've shown that f of x is g of x plus c, but c is negative g of a. Now all you have to do is plug in x equals b to get that f of b, well, what's f of b by definition? It's the integral from a to b, f of t dt. Well, actually right now there's no reason to use the dummy variable t. I may as well, because x is no longer in use in this formula, I may as well go back to writing x, my preferred choice of letter. F of b, the area under the graph between a and b, f of b, so I'm plugging in x equals b, it's g of b minus g of a, and that was this given antiderivative. That was our g, right, evaluated between a and b. That's the corollary. Okay, so I'm nearly at the point I want to stop. I should write one little note here. I've proved the corollary using the fundamental theorem of calculus, which depended on assuming that the function was continuous. But actually the corollary holds even without the continuous assumption. On f of x. So let's just look at the corollary again. I assumed that f of x was continuous. Actually, you can drop that assumption in this corollary. All you need is to be given some function which is indeed an antiderivative of your f of x. So you just need your f of x to be integrable and have some given antiderivative in front of you. And then this is still true. The area is the given antiderivative evaluated between a and b. You merely need integrable, but you have to be given an antiderivative for it to make sense. I've proved the corollary in a kind of a cheap way using the first version of the fundamental theorem of calculus, but actually there's a slightly stronger form of this corollary where you can drop the word continuous, but that needs to be proved in a slightly different way, so I'm not going to go into that. Okay.